questions pending from either HC Verma or from the module, you can let me know. We will discuss them. And there are some extra things that I want to discuss in work by energy beyond the doubts. Just let me finish the doubts first, then we'll discuss those also. So let me just check up to where we have discussed the doubts in the last lecture. And accordingly, we will continue ahead. Okay, 41 and 43, yes, we'll discuss that from HC Verma. So these are two very important questions in the HC Verma problem set. Let's start with the discussion of these. Yeah, I think we had done up to 39 in the last lecture, right? So just give me a second. We'll start with question number 41 from HC Verma. Okay, Shweta, we'll do those two questions also. So let's start with question 41. I'm just putting the data of the question on the board. So block of mass 5 kg is suspended from the end of a vertical spring, which is stretched by 10 centimeters under the load of the block. Okay, so what is happening initially over here is that under the weight of the block, which is attached to the spring, the spring is experiencing an extension. So this is at rest initially, with gravity acting downwards. So the spring is showing some kind of an extension under the weight of the block, where that extension is given to us to be 10 centimeters. Okay. So that is the initial state. Now the block is given a sharp impulse from below, so that it develops an upward speed of 2 meters per second, and we have to find the maximum distance to which it rises. So from this initial state where it was at rest initially, now what we are doing next is we are giving it a sharp impact, or like a sharp blow, or what is called an impulse from below. So we apply a sharp impulse such that now it develops an initial velocity at t equal to 0 of 2 meters per second upwards. Okay. And the mass of the block is also given to us. It's 5 kg. So from this state we have to find the maximum height to which the block will rise. So before we apply work energy, the first thing we need to do is, from this data, we need to find out the spring constant. How much is the spring constant? So initially, when the block is at rest, before we apply the impulse on it, the spring force is kx naught and the gravitational force is mg. So because the block is at rest in equilibrium, kx naught is equal to mg. So k into 10 centimeters is equal to 5 into 10 newtons. So the spring constant is 5 newtons per centimeter, or 500 newtons per meter. So that's the first thing. We need to find out the spring constant, so that we've done. And once you've done that, now what we will do is, from this state to the position at the highest point for the block. So this was, let's say, the initial state. From here, the block is going to a highest point over here, where the speed becomes 0. Whereas here it started with the speed v naught. Okay. So here, suppose the spring was like this. Now suppose we assume that the spring is compressed here, suppose. So now the spring is having a compression of x, whereas here the spring was having an extension of x naught. So between this state and this state, what is the height through which the block is climbing? That is the change in length of the spring. Okay, so it is L plus x naught, that was the initial length, minus L minus x, that's the final length. So x naught plus x, that is the vertical displacement of the block. So that is the vertical displacement. Okay. So now at the highest point, what is happening? The block will be at rest. Momentarily, it will just stop for a moment before it then starts descending. Okay, so V is equal to 0 at the highest point, which you can see over here. Okay, so from the initial state to the highest point, we just apply conservation of mechanical energy. You understood this? So what we have to do now to solve for this highest point, we have to apply work energy theorem and conservation of mechanical energy for the system from this initial state to this final state. Okay. As the block is going from the initial speed v naught to the final speed of 0, where it stops for a moment at the highest point. Then the spring changes its state from extension of 10 centimeters to compression of some unknown value x. And also the gravitational potential energy is changing. So between this initial state and this highest point final state, we have to apply conservation of mechanical energy. So change in kinetic energy plus change in gravitational potential energy plus change in spring's elastic potential energy. The sum of these three quantities should be 0. So just try to apply that and make an equation next up. So make these two diagrams and write the equation for conservation of mechanical energy. I'll put up the equation very soon and then we'll solve it to find out this maximum height. Okay, so if you've written down the equation, let's write down the equation for the change in the conservation of mechanical energy. We write down the equation from this state, let's say A to this state B. So the change in kinetic energy plus change in elastic potential energy of the spring plus change in gravitational potential energy should be zero. So the change in kinetic energy is minus half mv naught square. Change in elastic potential energy of the spring is half k x square minus x naught square, and this is plus mgh, and of course h is equal to x naught plus x. So we have this equation. This equation, okay. So in this we will substitute mg as 50, and we will substitute x naught as 10 centimeters or zero point 0.1 meters. Okay. And we will substitute k as 500 newtons per meter, and v naught was I think 2 meters per second, right? So this all data we'll have to substitute. Yeah, v naught is 2 meters per second, 5 kg and all that. So this becomes minus half into 5 into 2 square, so minus 10 plus 250 into x square minus zero point 0.1 square plus 50 into zero point 0.1 plus x is equal to 0. So we'll get this kind of a quadratic equation. 250x square plus 50x, and then this will be plus 5, okay, minus 0.01 into, so minus 2.5 minus 10. So that's how much now? That's minus 7.5, is it? Yeah, should be see. Yes, stage 7.5 कैसे है? ये सारे कांस्टेंट टर्म्स है ना, -10 है, and then minus 250 into 0.01, so that's minus 2, oh sorry, minus, yeah, 250 into 0.01, so that's minus 2.5, and from here 50 into zero point 0.1, so that's plus 5. So that's how we got that. So we'll take the positive root of x, so that will be 50 by 500, so 1 by 10. So we'll take this root. The negative root will be minus 15 by 50. No, see, there is this term, there is minus 10, okay. Then there is this term, 250 into, that's, okay. And then there is this term, 50 into zero point 0.1, so that's plus 5. Okay, so that's how the constant term is becoming minus 7.5. Okay. So this is the value you will take. The negative value will be the lowest point. This will be at the highest point. Now we have to find the height to which the block rises. So we have to go back and solve for h. So h was x naught plus x. So x naught itself was 0.1 and this is plus 0.1. So 0.2 meters or 20 centimeters is the height to which the block rises. So you have to be very precise with these type of calculations. That is the thing about JEE level questions. Not just the concept, but being able to apply the numerical calculations. You can do that also. You can take Karan, that's correct. You can take 2.5 as a common factor or 25 as a common factor. You can divide this whole thing by 25. This whole equation you can divide by 25 and simplify it. So it will become 10x square minus 2x, sorry, plus 2x minus 0.3 is equal to 0. So that probably you can factorize easily and do the question. Sum of the roots is minus 0.2 and the product of the roots is minus 0.03. So you can see that. Anyway, so how you choose to solve the quadratic equation, it's up to you. Okay, I have used the general method, which is by the discriminant method of solving. Minus b plus minus root of b square minus 4ac, that formula upon 2a. Okay, so let's move on to question 43 next. Now 43 is one of the key questions, also very important question to understand the application of work by energy. So let's discuss about that. So in 43rd, we have a rough inclined plane. Okay, like this, let's say. Whose angle of inclination with respect to the ground is given to us as 37 degrees, and also which has a spring attached at the bottom to a wall kind of thing. So let's say the spring is like this, and initially there's a block of mass m at the position A, let's say. Now this situation is such that at the position A, the block's distance with respect to the spring's tip, this distance is given to us as how much is it? 4.8 meters. And let's say this is the natural length of the spring here. So this natural length of the spring is not given to us, but we are going to make use of the fact that, and this is a rough surface, so we don't know the coefficient of friction, but it's a rough surface. And we also don't know the spring constant. So the spring has some constant K, which we don't know. That is given the block is released from rest. Okay. Then it goes on to compress the spring to a maximum compression of 20 centimeters. And then recoils. So the spring pushes it back, so the block recoils through a displacement of, how much is it? 1 meter, I think, right? Yeah, through a displacement of 1 meter up the incline. And mass of the block is also given to us, 2 kgs. So we have to take G as 10 meters per second square. The angle theta is given to us 37 degrees, and the mass of the block is given as 2 kgs. So from this information, we have to find the coefficient of friction and we have to find the spring constant. Okay, so this is a very good question to understand the application of work energy theorem in a complex system where almost all the different types of terms that we need to know are there. Like there is gravitational potential energy term, there is elastic potential energy term, there is work done by non-conservative force of friction playing a role here. So all these different kind of terms come into play. So just understand the parameters of the question, then we'll start discussing. Yeah, this is a proper JEE Advanced type of question. Okay. Okay, so now let's start understanding what happens after we release the block from that position. So we release the block at rest at the position A. Okay. Then what happens is that it slides down up to here, but by then it has some speed. So it's traveled through a distance of 4.8 meters. Okay, but the spring is still at natural length. So during this time, as it is sliding down, it has an acceleration of, or forget the acceleration, it's g sine theta minus mu g cos theta, but basically only gravitational force and friction are playing a role. Kinetic friction is acting like this, mg is acting like this, and normal reaction is acting like this. So you can see that normal reaction is, so let's say this state is B. So normal reaction throughout is mg cos theta. So kinetic friction throughout is mu mg cos theta in that. Now what happens after this is that from this state, where the block is just about to hit the spring at B, and the spring is at natural length. Now next, the block goes and pushes against the spring and compresses the spring. So this, now when this block comes to rest, let's say the state of the spring is, the state of the system is C. So this is at X. So at X equal to 20 centimeters, that is maximum compression. Okay, V is equal to 0. the block stops momentarily. Then of course the spring will push it back. So at the position C, you can see that at the position C, you can see the block is at rest, but the spring is pushing it. Okay, so it's going to have an acceleration upwards. So that's why it's going to recoil. Okay. So what we will do is we will apply work energy theorem from A to C, not A to B, but A to C. So if you look at the system from A right up to the state C, where the spring is having maximum compression. What is happening at A? The block started at rest. When it reached C also, the block has again come to rest. Okay. And the total displacement from A to C, you can see is this much. It is 4.8 plus 0.2, or it is 5 meters. Because A to B was the distance D. It was 4.8 meters. But now further it has gone another 20 centimeters. So the total displacement is this much, okay? And therefore the total vertical height through which it has climbed or it has come down, that is going to be S sine theta, or 5 into sine 37, so 3 meters. Okay. So when we are applying this conservation of, this work energy theorem from A to C, we will say, we'll take a system as the block plus the spring plus the earth. Okay. So there is no work done by external force, because normally action does not do work, but work done by non-conservative force is work done by friction, which will be minus of friction into displacement. So minus mu mg cos theta into s. Okay. And there is change in kinetic energy, but that's also zero, because u is 0 and v is 0 at A and at C. Change in gravitational potential energy is minus mgh, and change in elastic potential energy of the spring is plus half kx square. So work energy theorem, work done by external plus work done by non-conservative, is change in kinetic energy plus change in potential energy. So here it is the sum of two potential energies. Okay. So this is 0, but this is minus mu mgs. This is 0, this is plus half kx square, and this is minus mgh. So now just substitute the values. So this is minus of mu into 20 into 5. Sorry, mgs cos theta. I mistake. You can see here the work done by friction is the cos theta term also. So it's 0 minus mu into 20 into 5 into 4 by 5 cos 37. Okay. Plus half k 0.2 whole square minus 20 into 3. We just showed that the height is 3 meters. Okay. So the relation we are getting here is minus 80 mu is equal to 0.02 k minus 60. So this is our first equation. And it has two unknowns, k and mu. So we need to somehow generate a second equation. But for that, we'll use a second piece of information, that after the full compression at C, what happens? The block again recoils, and it recoils up the inclined plane by a distance of 1 meter. So just like we have written a work energy equation for A to C, now we'll write a work energy relation for after C, the block climbing up or recoiling up the incline through a distance of 1 meter. So we'll write another equation for that, and then we'll be able to solve the two equations for the two unknowns mu and k. Okay, so that is the method of solving this problem. So just note this down. and try to write the second equation yourself for what is happening after the maximum compression at C. So once you write that second equation, you will be able to solve for the two unknowns. So what I'd like you to do is, after going through this thing carefully and understanding how we got equation 1 for the first part of the motion, the block coming down the incline and then pushing the spring through 20 centimeters. Now you try to understand yourself how you'll write the equation for the second part of the motion. That is from the maximum compression of the spring to the recoil of the block happening up the inclined plane through 1 meter. So try to write that equation yourself. Okay, so I'll just verify. Yes, Tej, exactly. That's what we have to do. Next, we have to write the work energy relation between C and D. So what is happening is that the block started from here at A, okay. Then it went down to this position B, where it hit the spring with some velocity. Okay. Then it compressed the spring and came to rest at this position C. Now what is happening? The spring is pushing it back. So from C, we saw that the spring is pushing it back. So it will come back now in this direction. So it will come to some position like this, let's say D, where again it comes to rest. So the distance between these two positions, this is 1 meter. And while going up in this direction, again you can see kinetic friction is acting like this. Okay. So C to D, the displacement of the block is 1 meter. Okay. So again, work done by friction is change in kinetic energy plus change in spring's potential energy plus change in gravitational potential energy. So minus mu mg cos theta into S is equal to 0 because initial and final speeds are again 0 at C and D. But the spring's potential energy is becoming minus half kh square because when the block is at that position D, the spring is back to the natural length. Okay. When the block is at the position D at rest, the spring has now come back to natural length because the spring has released the block. So x is equal to 0. Whereas when it started, at that point of time, the spring was having a compression. So the spring's potential energy is changing from half kx square to 0 from C to D. So the change in potential energy of the spring is minus half kx square, and the change in gravitational potential energy is plus mgh, where this time h is this vertical displacement. Okay. From C to D, it is this vertical displacement. So this distance is 1 meter. This is 37 degrees. So this time it is 0.6 meters because S is equal to 1 meter. There we go. So minus mu into again 20 into 4 by 5 into 1 this time is equal to minus 250 into zero point 0.2 square. Oh, sorry, we don't know the value of pH. Minus k into. Now here remember x's value was 20 centimeters or 0.2 meters. So okay, plus 20 into h, which is 0.6 meters. So we get the equation minus 16 mu is equal to minus 0.02 k plus 12. This is our second equation. Now we will solve equation 1 and 2, and from that we will get the values of mu and k. You can see equation 1 was this, If we just do equation 1 plus equation 2, you will get minus 80 plus 16 mu is equal to minus 60 plus 12. So minus 66 mu, sorry, minus 64 mu is equal to minus 48. So mu will come out to be sorry, we are adding the two equations, so this will be plus only. My mistake. We are not subtracting the two equations, we are adding. So this will be minus 16. So minus 96 mu will come out to be minus 48. So mu is coming out to be 48 by 96 or 0.5. And then substitute that in any of the equations. For example, substitute that in the second equation. So minus 8 is equal to 12 minus 0.02 K. So 0.02 K will come out to be 20, or K will come out to be 1000 in SI units, so Newton per meter. So these two are my answers. Okay, so this is one of the important questions in this chapter in HC Verma. Like I said, from one question you can understand all the aspects of application of work energy theorem. Okay, next we will discuss question number 50. So just go through that carefully and explain to you how to work out that question. Yes, Didi, I'll scroll up. I'll also minimize a little so we can. Okay, so this is done, people. Okay, Diti, I'll scroll down. Yeah. So one equation we've written for the block coming from the initial position downwards till it compresses the spring to the maximum value. Then the next equation we are writing from that state of compression as the block is recoiling backwards and going up to the highest point again. So remember, it will go to a highest point which is not the same as the initial one because there is friction in the system which is dissipating energy. Agar friction nahi hota, then it would have gone back to the position A. But here, because friction is dissipating energy, so you can see that C is quite before A, or rather D is quite before A. The final point where it stops again, that point is D. In comparison to that, A would have been somewhere here because A was at a distance of 4.8 meters. So it doesn't come back all the way to A. Why? Because there is again friction which is dissipating energy. Yes, it would again stop at A. Na? Yes. What would happen is, see, if there was no friction, na, then mechanical energy would have been conserved. So it has to go to the highest point where it stops. So it has to have that same amount of gravitational potential energy. Na? So again, from lowest point to highest point, first your spring's elastic energy is converted to kinetic, and that kinetic is again converted to gravitational potential energy. So it has to go back exactly to that same point E. Okay, now let's come to question number 50, which is slightly more difficult type of question in terms of solving. So these last few questions are going to be trickier. Okay, so make sure you pay attention. So I'll just start with the diagram of the question. So you have a frictionless surface like this with a pulley attached on one side, standard fixed smooth pulley, and a thread going around the pulley. Now two blocks of identical mass. Please kgs. That's what I remember. The masses are same. Yeah, identical mass blocks A and B. So up till now the system looks very simple. Okay, but the added complication is going to be that there is a spring attached to the block A, which is initially in the vertical position like this, and that too at the natural length. So right now the spring is in a relaxed state at its natural length state. So here it's at a natural length state, and we release the system from rest from here. So we have to find the speed of the blocks at the instant when A loses contact with the surface. So I'll explain why A is going to lose contact also. Okay, now let's see the details which are given to us. Mass of each block is given as 320 grams or 0.32 kgs, and the spring constant is given to us as 40 newtons per meter. Okay. And this natural length of the spring is also given to us as 40 centimeters. And we have to take G as 10 meters per second square. And remember that this is a smooth surface, so there's no friction involved this time. Okay. So when we release it from here, what's going to happen is because of the tension pulling on this block, and the string is becoming tense because of the weight of this block B. What will happen is A will move towards the right, and as A moves towards the right, the system will go into some kind of state next like this, which I'm drawing below. It's going to reach some kind of a state like this where so now let's say it's reached this kind of position where the spring has got stretched because it's got pulled by the block A, because A has moved from its initial position through a displacement of S. So B has also moved from its initial position through a displacement of S downwards, and if A has picked up a speed V, then B has also picked up the same speed V. Okay. But more importantly, now the spring's length has got extended. So it has become L plus X, where we can see that L plus X whole square is equal to L square plus S square. Or if we take this angle as theta, we can see that L by S is equal to tan theta. See these equations, okay? Now we will apply the condition on the block A to lose contact, because we have to find V at the instant when A loses contact. When A loses contact with the surface. So the interesting thing here is to apply this condition that A is losing contact. We have to look at Newton's laws of motion very carefully in application. And at the same time, to understand the speed of the two blocks at this instant, we have to also understand the work by energy application or conservation of mechanical energy. So let's say this is the initial state here, and this is the final state. So for the system consisting of the blocks A plus B plus the spring plus the earth, for that system, change in kinetic energy plus change in elastic potential energy of the spring plus change in gravitational potential energy for B is equal to 0. Okay. So this is 2 times half mv square, the change in kinetic energy, okay, plus half kx square minus mgs is equal to 0. That's our first equation. Okay. Now remember, we have to solve for V, so we have to eliminate x and s, both the things over here. And the second thing we'll apply is for the block A to lose contact with the ground, the normal reaction on it must be 0. That should become 0. Okay. So for that, we'll make the free body diagram of A. So that is how we'll get our next equation. So make the free body diagram of A and find the condition for n to become 0. So just analyze the first and second diagram up to this point first and try to make the free body diagram of A yourself and see how we'll get the condition for normal reaction to become 0. The spring force acting on A is acting diagonally like this. It's acting, Kx is acting at an angle theta like that to the horizontal. So take that into account and find the condition for normal reaction to become 0. Okay. Yes, very good. That is the condition. So when it just becomes equal to mg, when kx sine theta just becomes equal to mg, yes, that is the instant when the contact will be lost. By the time it is greater than, so it's already jumped off. So just when it just about loses contact, at that moment itself, what is happening is that the spring force, which is going to be kx, okay, and the gravitational force, which is going to be mg, are going to have such a relation like this that the normal reaction becomes 0 because kx sine theta balances mg. This is the condition at the instant when contact is lost with the surface. Normal reaction just becomes 0 at that instant. Okay. So this equation tells us that x is equal to mg upon k sine theta. Okay. Now let's also look at the geometry of that triangle. This is the original length, which is 40 centimeters, we know. This is the displacement of the block, and this is the spring right now, which is L plus X. and this angle is theta. So you can see from this sine theta is equal to L upon L plus x, okay, or 1 by sine theta, so 1 plus x by L. So substitute that in this equation. So you get x is equal to mg by k into 1 plus x by n. So from this we can find out x first of all. Okay? So x is equal to, now mg was how much? 0.32 into 10 divided by the spring constant, which was, yeah, spring constant which was 40 newtons per meter, okay, into 1 plus x divided by L, which was 40 centimeters, so 0.4. So from this we'll get the value of x. So once we get that x is equal to 10 centimeters, now coming back to this triangle, you can see that in this triangle, this is 40 centimeters, okay, and this L plus x, that is now becoming 40 plus 10 or 50 centimeters. So you can see that this angle theta is sine inverse of 4 by 5 or 53 degrees. So now using this, we'll go back to, so we've got the value of x, we've got the value of theta. Now we can go back to our work energy equation and solve for V. So we'll also see that this S over here, S will become 30 centimeters because cos theta will be S upon L plus x. So 3 by 5 will be equal to S upon 50. You know S also. So going back to our work energy relation, 2 times half mv square plus half kx square minus mgs is equal to 0. So in this we know x now. We know s now. Okay. Now obviously we know mk. So we can find out the value of p. V is the only unknown. So we can find out. Okay, people. So hope this is clear. We'll move on to the next question, right? So next up, we'll do question number 62. In between, there are a lot of questions which are based on vertical circular motion and the condition for completing vertical circular motion, and that root 5 GR term and all that. Acha, 55 and 58 also. Okay, yeah, we'll discuss. No problem. Okay, so let's do question 55 first. So in 55, we are having first a straight track like this. Then it kind of ends up in a partly circular track. So that part circular track is like this, let's say. Okay, and of course at the end of the track here we have a spring attached to a wall. Okay. So everything is smooth. The track is smooth. The circular part of the track is also smooth. So suppose there is a small block that is just about against the spring initially like this. Okay. So the radius of this track is given to us as capital R. This radius is capital R, is all smooth. Now the block is pushed against the spring fixed at the left end and then released. Find the initial compression so that the block presses the track with a force mg when it reaches the point P. Now my guess is the point P is over here at the 90-degree position. This is the point P. So we want to find the condition so that the block reaches point P moving with some speed such that it presses the track, that is normal reaction, with normal reaction equal to mg, the force equal to mg. Okay, so that is what we want. So what we want is we will first compress the block against the spring. So we'll push it against the spring through a distance x and release it from rest. So the spring will push it and it will come here with some speed v naught, let's say. So we have half mv naught square is equal to half kx square. Okay, so that's the first part. Okay, and then as it is going from here, it reaches even this position with a speed v naught. But going in this part, it's in vertical circular motion. So by the time it reaches here, let's say the speed is v1. Okay, so this point is B and this point is A. So you can see that B to C, change in kinetic energy plus change in gravitational potential energy is zero. Whereas if this point was, some O before this, then O to A, we are using the fact that change in spring's elastic energy plus change in kinetic energy is zero. So from that we are getting this. Okay, so this far it is clear now. So far it is clear now. So now from B to P, B to the point P, okay, plus mgr, because you can see the height through which it is going is r. Okay, so that is 0. So further we have v is equal to square root of v naught square minus 2gr, and here we have v naught is equal to x into square root of k by n. So this was our second equation. Okay, now we want the condition for n to be, for normal reaction to be equal to mg at the point P. So for that, again, whenever we have a condition on a force, We have to make the free body diagram. FBD at the point P. We cannot do anything else. Work energy does not help us with force. Right? It helps us with kinetic energy, potential energy, etc. But for any condition of force, we need to make the free body diagram. So let's say this is the point P. So at that point of time, this tangential speed of the block is in this direction. So the centrifugal force acting on it is mv1 square by r. This speed I've taken as v1. So I'll write it as v1 over here. Okay. And that is what is pushing it against the wall. So the wall is applying normal reaction. Okay. So mg doesn't play a role in normal reaction. So at the point P, you can see that the normal reaction is equal to mv1 square by r. Okay. So for n to be equal to mg, mv1 square by r should be equal to mg. So v1 should be equal to root gr. Okay, so now substitute this in equation 2. So we get that v naught is equal to root 3 gr. When you just substitute that here, we'll get this. Okay, because v naught square is equal to v1 square plus 2 gr. And then substitute this in equation 1. So we'll get x is equal to root 3 gr into square root of m by k, or x is equal to square root of 3 mgr by k. Understood? No? Okay, good. So that is 54th question. Okay, so any question related to vertical circular motion, this is the general way of proceeding. One equation from conservation of energy, one equation from free body diagram, centrifugal force acting outwards, tangential force giving tangential acceleration or deceleration as be the case. So next we'll look at 58th problem. Yeah, see, the thing is centripetal and centrifugal cannot be used in the same sentence. When we use centrifugal, that means we are in the rotating frame. Okay, this is one very important concept over here. When you look at circular motion from the ground frame, okay, then a particle going around in circular path, for example, it has a centripetal acceleration of v square by r. Okay. So the net force should be equal to mass into acceleration. So the centripetal force should be equal to mv square by r towards the center. Okay. And next is we can look at circular motion from the rotating frame. Okay. So that means we are in the frame of the object that is doing circular motion. Okay. So in that frame, this particle experiences centrifugal force, which is mv naught square by r. If this is going at a speed v naught in the circular path. Okay, so this is a pseudo force. Okay. So now, whatever force is acting in this direction, that has to balance the centrifugal force. Whereas here, whatever external force is acting in this direction, it has to provide the centripetal acceleration. Okay. So ultimately, both of them give the same result, that the external force acting towards the center should be equal to mv naught square by r. but the way we are expressing it is slightly different. In one case, we are saying it balances centrifugal force. The other case, we are saying that it is equal to mass into centripetal acceleration. Let's move on to question 58 then next. Right, that's what we're doing. The next one, yeah. Okay, finish with this, then we'll move on to the next part. Okay, done with this now. Okay, now let's come to 58th question. So see, the main thing you have to understand in question 58 is that this this system is like this, like you have a string suspended from the point O, okay, which you are initially bringing to a position like this. So this is a massless thread with a particle attached at this end, which you initially bring to this position and release it. But more importantly, This is against a wall, and on the wall, at a certain point, which is vertically below the point O, vertically below the point O, at this point you have P is like a nail or a wooden peg coming out of the wall. Okay. So it's like you have this kind of situation. This is your wall. So from some point O on the wall, you suspended a string with that particle, but also there is a nail coming out at the point P from the surface of the wall. Understand? So when you release it from this position, this will have a tendency to, because of gravity, it will have a tangential acceleration like this. It will come in a circular path, and at some point of time, it will come and hit against the nail or the peg. So this will come in and hit against this. Okay. So from here to here, it has come in circular path. Okay. And thereafter, what will happen? It will wrap around the nail. So next part, the motion will become like this. Now it will start a new circular motion like this, about this point. So we're going to circle with a new radius. So if this distance is x, we're going to new radius of L minus x from here. Like this. This is the concept here. Yes, after hitting that nail, it starts wrapping around the nail. The string starts wrapping around that nail or that peg. So its circular motion center changes from O to the point P, to the peg P. Okay. So let's say this is the initial position A. So from A to B is a vertical circular motion with radius equal to L and center at O. But then from B to C or D or whatever, all these points, the rest of the motion is a circular motion with radius equal to L minus x and the center at P. Like this. So this is how we have to deal with. Yeah, radius will change. That's, you can see in the diagram the radius is changing. The radius has become L minus x. Okay. So for example, the first part, it's saying that now actually the diagram I've shown is wrong, because if it's starting from rest over here, it can never reach a position like this. It'll only reach a position on the other side where the height is the same. Okay. So it will stop at the position D. Okay. So the first part of the question, if bring it to a position like this over here and release it from here, then it will have to stop at the same height on the other side. But the quality of circular motion has become different. From here, it has now gone into a circular motion with a different curvature. यहाँ से इसका ऐसा curvature हो जाएगा. But the moment it reaches this position here, it will again stop, because work energy. So A to C, you can see that change in potential energy is 0. So change in kinetic energy should also be 0. So U is equal to 0 at A, which means that B will be equal to 0 at C. Is at the same vertical level. So that is what the first part is explaining, is asking you to explain. Okay. In the second part, it's a little bit more interesting. So in the second part, what we are doing is x is equal to L by 2. And we are taking it initially to this position, the 90-degree position. So from this point, we are releasing it from rest. So what will happen is by the time it comes to hit the nail or the peg, it's like this. And this mass M now, it has a speed, let's say V naught. So that V naught is root 2 GL. Because again, if you see A to B, half mv naught square minus mgl is equal to 0, because this total length is L. Okay. But then what happens? The radius of the circular path changes to L by 2. Okay. So the radius is becoming L by 2. So in terms of radius, this V naught is how much? It is 2g into 2r. So it is 2 root gr. Now you can see that 2 root gr is less than root 5 gr, but greater than root 2 gr. Okay. So it will cross this 90-degree position, but somewhere over here, what will happen? The string will slacken. The tension in the string will become 0. Reach some position here V, where this angle is theta, this angle is theta. So the tension will become 0 at this point, because mv square by r is becoming equal to mg cos theta. Okay. And let's say this position is C. So B to C, if you apply work energy theorem, then again you can see that half mv square minus v naught square plus mgh is equal to 0. Now that height is going to be this whole value, this height. Okay. So you can see that h is equal to r plus r cos theta. So v square is equal to v naught square minus 2gr into 1 plus cos theta. So this is our second equation, this is our first equation. So from this we are getting that v square is equal to gr cos theta. And from this we are getting this. So solving the two equations, we get this relation. And in this we'll just substitute this one. So we'll get cos theta. So at this position, the thread will slacken. It loses tension. Okay, so that height you can find out from here. Okay. So R was L by 2 and cos theta is 2 by 3. So 5 by 6 L. That should become the height. Okay. No. Diti, it wraps around the nail from the position B. From B to C, the string is wrapping around the nail only. But at C, the string becomes slack. You understanding? Man? The moment the string hits the nail, na, from that time onwards, so it hits the nail when the string becomes vertical. So as the particle is crossing the point B, the string is now starting to go around the nail. Na? But initially there is tension in the string. Whereas by the time it reaches the point C, the string becomes slack. Okay. Okay, so we more or less completed work energy, but about an hour or so in the next lecture, we will discuss some more problem solving methods for advanced questions and few more questions from HCV and the module we'll discuss. Okay, so that's it for today's session, people. Wish you all the best. Okay. Start wrapping up work by energy. Start trying to work out maximum questions from the module also apart from HCV. So wish you all the best. That's it for today, people.